All right, welcome back to the channel, everybody. Thanks for joining us. Today we're going to do something a little different. I'm going to give a talk that I just gave at the Low Temperature Detectors Conference in Santa Fe, New Mexico. So this is going to be a talk aimed at a professional audience of low temperature detector experts. I'll try to spend a little more time explaining in some places, but unfortunately, this one's going to require a little more physics background to understand. So if you're interested in seeing like what we do on a nitty-gritty basis, this talk should be for you. Also, this talk was designed to like help people who are new to the field not make the same dumb mistakes that I've been making for the last 25 years. So we're titling it Microwave Kinetic Inductance Detectors, What Not to Do. First, I'm going to give you a brief introduction to MKID Physics. Then we're going to go into the what not to do relating to design, fab, and readout. Those are the places where I see a lot of new people making mistakes. So let's just launch in. So first, what is an MKID and how do these things work? An MKID's a superconducting detector. That means it can count single photons and tell you their energy. We do this through using a superconductor. So what we do is we make a little LC oscillator. So this is a simple harmonic oscillator. You can think about it the electrical equivalent of hanging a mass on a spring. And when a photon hits the inductor of our detectors because of some effects of superconductivity, the inductance changes. This is equivalent to, say, changing the mass on the end of that spring that you're that's oscillating. It'll change the resonant frequency. That's what happens with our devices. A photon hits it and the resonant frequency changes. So we plot this as a change in the resonant, in the phase and amplitude of a microwave signal transmitted past the resonator. This is the equivalent circuit on the left. See, we have an inductor and a capacitor. They're hooked up together with a little coupling capacitor that shoots in, that couples power in from the outside. When a photon hits this inductor, its inductance changes, and that causes the resonant frequency to move to lower frequencies. So the microwave probe tone we're sending past this resonator goes from this solid line in this plot of frequency versus transmitted power to the dotted line. That change is what we detect, and it essentially encodes the energy and arrival time of each photon in the phase of this microwave probe signal that we then use warm room temperature electronics to read out. On the top left shows you what we get. So this is a real event where we have a photon hitting a resonator and we get this pulse out of it. So that's what a photon looks like when it hits one of our detectors, this phase pulse. You can see that it's got this very sharp rise time. That tells us when the photon hit, to about 100 nanoseconds. We also have this fall time and all the signal and noise in this pulse. And what happens is the height of this pulse tells us the photon energy. So a blue photon gives us a big event and a red photon gives us a small event. So you can see on the bottom here what this looks like when we illuminate one of our resonators with lasers going all the way from the ultraviolet here to the near infrared here. And when we illuminate them with a laser that has a narrow response, we get these histograms. So this shows us that what we've made here is not just a detector, but a spectrometer. We can tell the energy of every photon that hit it. There are also versions of MKIDs that work in the X-ray and in the far infrared and sub-millimeter, as you can see here on the right. One of the things we have to contend with is that we have to deal with athermal phonon loss. This is a complicated process where the energy that we want to get into the detector manages to seep out into the substrate before it does its job of breaking these charge carriers of superconductivity called Cooper pairs. So we have to spend a lot of effort trying to keep all the energy into the superconducting layer. The real strength of MKIDs is their multiplexing. Multiplexing is their real, the thing that really distinguishes them from other technologies that can detect single photons. So this is an example of where we can take many of these MKIDs and hang them off the same wire. And since each one has a different resonant frequency, they basically don't interact with each other. So we can send in a comb of microwave frequencies, one to hit each resonator, and then demodulate them at room temperature. This is very similar to what a cell phone base station does. And in fact, we use a lot of the same technology that cell phone base stations use. All right, so let's get into the meat of what not to do. So when you're designing an MKID, what are the common mistakes that you can make? there's three main resonator architectures that you can choose. The first is a transmission line resonator. You can see that up on the left-hand side here. This is the first ones that we published around 2003. This shows a coplanar waveguide transmission line resonator. It's a quarter wavelength long. This is a common and popular and easy way to make an MKID. The second way is a lumped element MKID, which you can see here. This is in a transmission line, you have a distributed inductance and capacitance, while in a lumped element, you have basically separate inductors and capacitors. So here you have the inductor, this meandered structure here, and then you have a capacitor, these interdigitated fingers. This is the way most of our MKIDs right now work. Finally, you could do a cavity or a waveguide solution like the one shown here. No one's actually done it, so it would be interesting to see, but I don't think it's the best for a photon detector. In general, I prefer the lumped element design here. It's much smaller than these coplanar waveguides, and it's a little easier to tune the frequencies. And since these inductors, these transmission line MKIDs tend to be really big, they tend to disconnect your ground planes electrically, which is a bad thing. So I would, if you're starting from scratch, I definitely recommend lumped elements unless there's a really good reason that you don't want to use them. All right, so what about inductors? A lot of times people just want to take a meander and go straight back and forth. This is really a nightmare for electromagnetic coupling. You really want to make a double meander where you take the wire, bend it in half, and then meander it. The reason for that is that there's currents flowing in these wires which create magnetic fields. So by having the right next to one current, you have another current going the opposite direction in the double meander. This cancels out the magnetic field mostly and reduces the electromagnetic interaction of one resonator to the next. This is really important. For capacitors, you basically have two choices. You can make interdigitated capacitors like the one shown here where you have just fingers interlocking, or you can try to make a parallel plate capacitor with a dielectric between it. The problem is these dielectrics are really lossy. Some people have made amorphous silicon work. The loss is still much higher than the crystalline dielectrics you get on these interdigitated resonators. However, most people don't have access to that amorphous silicon process, and if you're starting from scratch, you really don't want to go with these capacitors unless you know what you're doing. And I still think you may see extra TLS noise from the deposited dielectrics. So avoid those if you can. Okay, the next thing is feed lines. These are the wires that get the signals into and out of the array. There's a couple obvious options here. The first are coplanar waveguides. This is what most people use. It's basically, you can think about it as a coaxial cable. It's cut in half to some extent. It's the flat version of a coax, basically. It has a center strip that carries the signal and ground planes on either side. You could also do a microstrip where you have a microstrip is a metal with a dielectric and then a ground plane underneath it. That works. There's other possible geometries like slot lines and strip lines. So microstrip can work. It turns out that it's kind of hard to couple to for a variety of reasons about the fab. The slot lines and strip lines tend not to work because they tend to have other modes, like they can have microstrip modes that can be a problem. I think unless you have a really good reason, you should go with the coplanar waveguide structures, and you must have crossovers. So here's an example on the left of an air bridge that we made at Lincoln Labs. This kind of structure is vital to basically tie the ground planes together. You can get unwanted modes where you can go from the coplanar waveguide mode where the ground planes are at zero potential and the center strip kind of voltage goes up and down, to these slot line modes where you kind of wobble back and forth. And that has totally different coupling and transmission, and it screws everything up. So you have to have these air bridge crossovers to tie your ground planes together. And it turns out you need more of these than you think you do. For whatever reason, our Sonnet sims don't accurately capture the problems of these ground plane crossovers. So you need more than you think, maybe even one every couple resonators. Okay, finally, you have to think about resonator frequency placement. The resonators want to be, if they're too close to each other physically, then they'll push each other away in frequency space, which isn't good. But if they're too far apart from each other, they also have problems because you end up with the film varying, and so their resonant frequencies are scattered because of that. So there's a game of trying to put them close enough together that they're nearby for film properties, but not too far. So you need to be smart about this and think about it carefully and simulate it all with a EM simulator like Sonnet or HFSS or something. All right, what not to do with fabrication. So the first and most important choice in fab is probably what substrate to use. Everyone's first choice is going to be silicon because everyone uses it for everything. High resistivity silicon is excellent. You can get 10 kilo ohm centimeter resistivities. It's not very expensive. It's single crystalline, super low impurity densities. It allows deep etching like silicon micromachining. This comes with downsides. So the problem with silicon is fundamentally that it's a semiconductor, which means that when photons hit it, they free electrons, and those electrons essentially last forever at the low temperatures we operate at. And these free charge carriers can interact with the resonator. They also can fall into charge traps and then come out later. We've seen this give two-level system noise, and we've seen it have effects where the resonators almost act like an ion trap, where electrons get trapped in the electromagnetic field of a resonator and then slosh back and forth, causing the pixels to go hot. This is an example here where we have this pixel selected right here in blue, and it was perfectly fine through a lot of these observations, and then it just started going nuts. This is an example of what happens. And we see this happen every time we use silicon. And even if you're not working in a wavelength where photons are supposed to be able to break the to free electrons in silicon, there's still cosmic ray events that create these free electrons. There's just too much physics going on in a semiconductor. So we use sapphire, aluminum oxide, Al2O3. You can buy very high quality single crystal sapphire substrates. They're not much more expensive than silicon, and they get rid of all of these problems. Highly recommend sapphire. Everything else turns out to be terrible. We tried germanium and quartz and a bunch of other materials, some of them single crystal, and none of them have worked well. We've had a lot of excess loss and two-level system noise from it. So be very wary about trying anything else besides silicon and sapphire. All right, the metals are a whole talk by itself. Superconducting metals are complicated. They often don't have the properties you want, and you have a very limited choice of them. I actually wrote an entire book chapter on it, which is available here at this link. The sensor material, bottom line, is you have two main choices. You can use aluminum, which is pretty standard. It's low kinetic inductance, so that means you end up having to make the aluminum very thin, which makes it delicate. It likes to oxidize. It also reflects 93% of the photons that hit it. So aluminum works in some bands, far infrared, some millimeter, but in the optical and UV, where I tend to work, we usually default to something else. But every other material has its own challenges. My advice is to use hafnium as long as you have a dilution refrigerator that can get below 35 millikelvin. If you don't have access to hafnium or don't have a fridge that can get cold enough, there's other materials that you can use, like platinum silicide, that might, or tinitride, that may work for you. But you have to think carefully about it. We have had trouble with compound superconductors, so things like tinitride and platinum silicide, where there's two components, and even when you have two components, it turns out to be hard to keep them tuned up because the superconducting metals are just really the most critical part of making one of these. UHV depositions are often critical in this, so you need a very clean sputter system with low base pressure. All right, so let's get into some of these fab issues. So my first rule of fab: don't believe it until you see it on two different wafers. We have seen some incredibly strange things over the years come out of the fab, and you never know what someone's put in the fab before you or what can go wrong with your process. So if you want to, before you waste your time looking at something weird, make sure you can reproduce it. The capacitor metal always needs to go down first and on a clean wafer. This is important. The capacitor has high electric fields, and it interacts with surface things like surface impurities, OH on the surface. All those things, and defects and impurities on the surface are really important, and the fields are highest between the capacitor metal and the substrate. So you really want to put the capacitor down first and make sure the wafer's as clean as you can get it. To make anything work, you need to get the sensor metal deposition, etching, packaging, cooling, and readout right, just to read out a single layer MKID. So if things aren't working, it could be any of those things, which makes it harder to diagnose. Come talk to us if you are struggling. Okay, the sensor metal and substrate should see as little plasma as possible. Plasma seems to roughen the metals and do bad things to its loss parameters. So we try to avoid it as much as possible. If we can't avoid plasma for our etches, we tend to use metal protection layers to keep the metal protected from that plasma in a way that can be removed later, usually with a wet etch. And this is important when you're going from single devices to multi-layer devices, which you almost always have to do for things like ground plane crossovers and heat sinking. So you need to be careful to design a process flow that protects especially the capacitor of your MKID and the inductor too, if you can manage it. You got to watch out for etch residues. You can often get polymers that redeposit on in the slots of your capacitor. Those can lead to excess loss. Feed lines, those wires that bring the signals into and out, they have to have those crossovers. They're also like 0.5 meter long when you unwind them, with 2 slots that are each 2 microns wide in our design that can't have any opens or shorts. It turns out the feed line fab quality control gets us more often than other things in this. It's one of the hardest things is to get your feed line yield good. That's why we've been working with Lincoln Labs with those AirBridge devices, which have had nearly perfect yield. Okay, number 9, don't go too high resistivity. So we've spent a lot of time, and our European colleagues at SRON have spent a lot of time trying to work with beta tantalum, which is a phase of tantalum that has its TC between like 600 millikelvin and 1 Kelvin, depending how you deposit it. It has extremely high resistivity, and that has caused a very short lifetime. So watch out for material that are for very high resistivity materials. Anything above sort of 20 picohenries per square, or maybe 200 microohm centimeters, I would start worrying about. Make sure your resonator frequency spacing lets you identify resonators, even if many are missing. This is really important. A lot of times you'll design a mask, and you'll measure like 7 resonators, but there should be 14. And so then you have to figure out what you're looking at. And that can be really hard. So think a lot about your frequency coding before you design your resonator, so that even if resonators are missing, you can figure out what's what. You always should include test structures on your masks. Things go wrong all the time in the fab. It's the hardest thing we do. The test structures will help you figure it out. This one's less obvious, number 13, but your fab and test loops need to be fast enough to fix one problem before something else drifts and causes a new problem. There's always new problems arising in the fab, so you need to fix one before another one arises. And if you don't do that, you may never converge to a working device. So you need to be able to make the device and test it pretty quickly. Control what goes into your UHV deposition systems for sensor metals. You really need to control your metals. That first metal layer, the sensor layer for the MKID, is just really important. And finally, good practice for everyone, keep good logs. All right, what not to do for readout. So we've developed 3 generations of FPGA-based readouts. Readout turns out to be way harder than you think it is. Each one of our readouts, despite the previous experience, took 5 to 10 person years of effort, maybe more. Some of these where we didn't develop much new hardware at all, but used off-the-shelf hardware. The software programming is that complicated. So if you're thinking about making your own readout, only do this if you're a masochist and have talented FPGA programmers and RF engineers in it for the long haul who won't disappear as soon as the first version's delivered. If you don't want to make your own, and this is smart, talk to us at UCSB or ASU or T0 Technologies or someone about some of the readouts that have already been developed. Finally, parametric amplifiers seem to be the key to future MKID performance gains, but we need to do a lot of miniaturization. This picture is from my lab. These are two chains of parametric amplifiers, and they're quite large. This is about the size of a shoebox. So we're currently working to shrink all this down into a single box, but that's really important. Also, think hard about before you make something too complicated for the for your readout. There are performance gains to be had by more exotic readouts like multi-tone readouts and tone tracking and running the resonators into saturation, but these are hard to make reliable for regular use on an instrument. All right, so my closing thoughts. MKIDs are a fairly mature technology with wide potential applications for photon counting and photon detection, all the way from the X-ray and gamma ray to the far infrared and submillimeter. But they're too tall poles for new users. The system complexity and array availability. As a community, we need to work on both. Fab is a continuing problem. Research fabs are often not clean and stable enough, but we're too small volume and use non-standard materials for production fabs. So we need to keep working on that fab problem. Also, we need this work to continue happening at universities. Universities are the only place we produce new low temperature detector scientists. And so we can't centralize everything in national labs. Finally, workforce issues continue due to quantum computing firms hiring everybody and a poor funding climate. All right, so that's my presentation on what not to do. I hope you learned some lessons and don't make some of the dumb mistakes we have. And I look forward to all the excellent MKIDs you'll create in the future. Thank you.